All right, so this homework, let's see, I haven't looked at it recently. It's 3 parts, right? Any questions on this thing? What's going on? All right, equation 1 involves the structure factor and the form factor. Okay, so he's got so it looks like a really complicated equation instead of just P times S, like I is P times S. So S is the crystallography part of it, and P is whatever the thing is that's on the lattice side of the crystal. So anyway, the reason he has this more complicated is because he has this polydispersity in it. So he has, if he doesn't have polydispersity, the things will crystallize and we can't get the what he's trying to get, which is like this kind of correlation function for the particles. So he makes them polydisperse, and when he does that, he thinks he has to do this alpha beta, like, so you have one particle, one size, so all the particles are different sizes. You have to take every pair of particles, like particle, including the pairs of the same particle, like particle 1, then particle 1, particle 2, particle 1, particle 3. Right, so alpha, beta, like particle 1, particle 2. So that's the concentration of the ones, concentration of the twos, and just the X is a polydispersity distribution. So the concentration of the different size particles, like in other words, number versus size is a distribution, which is this Schultz-Flory distribution thing that was using. So in each of those particles has a different contrast, because this contrast is going to be like the scattering density times the volume. And if they're a different size, they have a different volume. This B is going to be a different volume. So that'd be the rho, it'd be like the volume times the density. This is called rho. And then this is a Fourier transform of that distribution in space. That gives you a Q scattering factor. So this is just a Fourier transform for the case where you have, normally this would be e to the I Q dot R for 2 vectors. But if you rotationally average the particle, then you end up, then the exponential I Q dot R becomes the sine. It's called a SI function, a psi function, sine over the value of the argument. So that exponential becomes a psi function. These aren't vectors anymore, they're scalars. So that's for a rotationally averaged, Fourier transform for a rotationally averaged particle to give you the Q amplitude. You have to square the amplitude to get the intensity, because the amplitude can go plus minus. So the intensity only goes plus. And it's a binary interference. You need to have something times something, A times B, the binary, right? 2 things. So she has B alpha, B beta. And this sum, this is really a double sum. So that's kind of where that is.
So normally that B2 term wouldn't be as complicated in like a normal interaction, or would it always be hard?
No, this is standard. This is just like the Fourier transform. It's just you wouldn't have alpha beta, it would just be B squared. You'd assume they were all the same. In fact, he kind of does that in the end. So this is a little bit of a, he didn't need to do that exactly. Because in the end, he says, he gets the structure mean, I guess, is using the mean, mean B squared. So he doesn't have alpha beta, he just says they're all the same. And if it's a small polydispersity, you just assume they're the same. And this would be the experimentally measured one, because experimentally he measures the scattering. So in the dilute solution, S is 1. So there's no structure in the dilute solution, so S goes to 1. Right. So in that case, when you measure the dilute solution, you just measure the B squared part, the form factor, which would be P, capital P in the other thing. So if you can measure capital P, then you just divide I by P, you get S. And that's what this SM is. S divided by the mean B gives this thing. So in the case of the correlations, he's still calculating the different size ones differently. So so he's calculating, like, rather than saying the form factor of one and the other, he's saying like the positions. So he forgets about the size of them, but the positions are different for each one because they're different sizes. That's the idea. So a big one would be smaller than a small one. So that means that the structure factor will be different between a small one and a large one, or a large one and a large one. So that's why he still includes it here. Right. So when he goes to compare to the data, because he calculated data that way, then this is the right function to get the data, not this function, not the S total function, which S total assumes that what is it? S total, I think, assumes, what is S total? I never remember this. I mean, it's like the third time I've looked at it. Measure for the overall local ordering of suspension, irrespective of the sizes and shapes. So S total would be if you could ignore that the big ones correlate differently with big ones than with small ones. So that's just the standard correlation function, I guess. So this one has different sizes, that one doesn't. So then when he does the comparison of the data, he finds out that the SM, one where you just divide, which is what he did to get the data, matches the data, and the one S total, ignoring the size differences, has kind of a problem. Then you get to the second order and third order. So this is kind of like more or less like the correlations, like so you have spheres coming up, and then there's going to be like a correlation hole because they can't pass through each other. So that's going to be like the radius. So you kind of have the radius of the sphere here or here. So that's because it can't get into the other sphere. That's excluded volume. Then because of that, the things that would have been in the other sphere pile up at the surface. They were randomly distributed, but then you say they can't be here, so they have to move. So they move over to be around it. So that's the first order shell. And then there's another, so this repeats, like, in other words, if they're piled up at the surface, then you have actually another kind of larger excluded volume that excludes to the next shell. So that's this one. Then the ones that were excluded from that pile up on the outside of that. That's the second order interaction. Then that repeats ad infinitum until you get to one, where the structure factor is one, you have no ordering at long distances. Like when you're at the particle and you go out forever away, like there's no relationship between the particle there and the particle where you are. So it has to go to one. This goes to one. And you can see this guy goes plus and well, it goes down to zero, right? So anyway, so that's how correlation functions work. It kind of describes the organization of things, but it isn't exactly. Now, it's two things that were different could give the same correlation function, put it that way. It doesn't say that this thing, so it's only a vector quantity, so you can't give a 3D mapping of the thing exactly. It's kind of odd that this thing isn't giving you actually the structure. In other words, you can't take this and then draw a picture of what the thing is. But you can't, so it's like an average, like a mean thing. So you're going to get mean information like density. Density's high, some distance, but it doesn't tell you what the actual crystal structure is. You can use a model and then analyze this and then get the crystal structure, but it depends on the model. And you could use more than one model to get the same answer.
Is that one kind of with part E? Was that kind of what part E was talking about on the homework?
I don't think I asked that, but that's called phase information. In other words, you have the correlation function. If you want to put together the thing, you need what's called phase information, which would be like the amplitude function. So in other words, and you can't measure the amplitude, you measure the intensity. This is a thing that goes on in scattering and diffraction. Phase information, they call it. So you lose phase information in this measurement, meaning you can't put the thing back together. Like you could, when you put Humpty Dumpty, his feet would be on his head, but it would still have the same correlation function. So what is it, part E?
Yeah, I was talking about I think it's talking.
No, this is just, no, I mean, it's good what you're thinking, but basically no. So this is just, so he does this kind of screwy thing. So, all right, so he gets the theory, and then he has to rescale it to match the data. So he has to multiply this thing by a number. The number is smaller than one when you're below some volume fraction, and larger than one. Let's see, no, it's larger than one when you're below and smaller than one. So he has to raise it when he's at low concentration and drop it when he's at high concentration. But at some point it's one. That means his theory works there. And then he's also got this problem that when he see that dashed line's a little bit off from that peak. And this is something that happens a lot with correlation functions. Like you have your model thing and then something happens to the second order peak, it doesn't match, you know. So if you did a least squares fit, it would give you the wrong number. You know, so he has to have another fudge factor that leaves this peak where it is, but shifts this peak either over to the left or to the right, to a larger and smaller. It means the next order is either packing tighter or packing further apart. If it's smaller, it means it's packing closer. If it's larger, it means it's packing farther apart. So that means that and that's probably more important than the amplitude. So basically, something's going on with the packing, right? And that happens to work out when he gets to one. Right. So this is pretty complicated. Like this is like kind of not that obvious what's going on, but there is a magic number of 45% volume fraction. Right, there's some magic number where all the stars align and everything works out just the way it's supposed to. Right, so you don't know anything about this basically except 45%. So offhand, like 45% doesn't mean anything. If you have monodispersed spheres, they percolate. So if you randomly arrange monodispersed spheres and keep increasing the concentration, at some point, there'll be a pathway through it, a conductive pathway through it. That's called the percolation point. So basically, you could run an electric current through the collection of spheres when you reach 31%. That's a magic number. And then there's another magic number. There might be other magic numbers, but another volume fraction is if you take marbles, monodispersed spheres, shake them up, and then they'll make like a perfect HCP lattice, if you ever look at that. You know, or also if you look at this first came up, I think it was like one of the British scientists figured this out because it had to do with warfare. So they had cannonballs and they had to figure out the best way to stack cannonballs. Like, so you could, I don't know, put more cannonballs in a small area or something. This was apparently the technological advantage of the British over the French or something. So anyway, they found out that they would either go HCP or FCC. And then they figured out that the volume fraction would be like 72%. And so if you want to store the cannonball in the smallest possible space, like simple cubic wouldn't be the way to do it. That has a volume fraction of like 60%, I think.
Just to reduce like the space in between.
Right, yeah. And also things if they're making a crystal, they have an attractive enthalpic interaction. So they want to get as much of that as they can. So they want to get as close as they can get, you know. So basically 72% is it. You can't do better with spheres. If you have sheets, so if you're packing something like rods or sheets, you can get much higher, right? I mean, rods, because one dimension you can fully pack. And then with sheets, you can get actually a 3D packing because they can just stack on top of each other, right? So it depends on the dimensionality of the object too. The 72 is magic for spheres. So if you think about polydispersity or asymmetry, that's going to lower that number, you know. So polydispersed, anything you do is going to lower the number. Spheres are perfect. Everything else will have lower volume fraction of packing, or a higher. Let's see. I guess maybe it's higher because you go towards a rod, it would get higher. Anyway, my idea was that it would be lower, like you would get to somehow 45. So maybe 45 is a percolation, or maybe it's something else. If you can figure out whatever you think it is, you know. But he doesn't say. He just says like, there's a magic number, 45. So the question is like, what is that? There might be some other things about packing spheres that you can come up with. This is basically an open-ended question. I think polydispersity would give you a higher packing fraction. You can Google it. Do polydispersed spheres pack denser than monodispersed spheres? That's probably been answered by somebody. It's pretty easy to do. You just get polydispersed marbles and weigh it. Yeah, be kind of easy to do. they have to pack denser, right? Because the small ones can fill in the holes. Like if you think about tiny ones that would fit in the void space. Anyway, so yeah, so that's that. Any other things here? I said this already, like this, he plots the three things. The one kind of works, but he needs the two fudge factors. And then this business is where he goes into crazy land, I think, the way I see it. But I mean, I could be wrong, you know, because I just kind of glanced at it. But so this is what I would bring up if I reviewed it, though. So yeah, so there's a problem. There's a big problem with the whole thing he does here. Like he shows the scheme of making this. So the thing, so he even shows that the middle PMMA is soluble in the Decalin tetralin mixture. So that means why it isn't pure blue in here. Some of the yellow goes in, dilutes it, and he thinks there's a gradient. So this is all part of his model. In other words, he fit the data with that model. It doesn't mean it's true. Like the fitting scattering data, there can be many models that fit the data. And you can see, well, there's some features he's getting that seems to be pretty good, but it might be other reasons. For instance, reversing the gradient can sometimes give you the same curve, you know, things like that. So basically, it isn't necessarily true that this model's true. You know? So, but basically, he's got this idea that the inner part is swelling in the solvent and the other part is insoluble, meaning that it's a melt. Like it's basically, if you put polystyrene into water, it's solid polystyrene. It's got Gaussian chains, dimension 2, right? And he says in here that the fully stretched out PDMS chains, the length of that comes pretty close to the width of this thing, which isn't, if it's a solid PDMS melt, it's not going to be extended chains. The only reason it would be extended chains is if it was in a solvent, right? So that seems pretty weird. And then as he increases the volume fraction, that shell thickness drops, like based on 1 point, which he says has no error bar. He gives the error bars. So, but it still isn't anywhere near if you calculate what the Gaussian chain size for PDMS is, meaning that this thing has to be a multi-layer. I guess. I think this is 35, and I think the size is like less than 10. So there's at least 4 PDMS coils in the diameter of that thing. If you want to look at it that way. That means that, so 4 coils away, that chain isn't attached to the PMMA, it's just sitting there as like paint. It's kind of like paint on the PMMA. So this whole model of having these surfactant modified particles that allows it to be a colloid is really weird. The whole thing's weird. It doesn't make that much sense, actually. Like, it wouldn't suspend in that case. These things would just cluster together and then precipitate out. Because so you would never see, the soluble PMMA would never see the solvent because it's coated with paint. So, you know, this whole thing when you start looking at it closely and things start falling apart. And it's, for me, the place where it started falling apart was right here, because I thought he's saying this thing collapses. So why would that shell collapse when it's looking at more of the same thing? In other words, these chains on the surface are looking at other chains on the surface that are the same polymer, so they should have an affinity, so that they should expand, not collapse. And then once you start looking at it and say, he never says like what's soluble and what. The assumption is that PDMS is soluble in the Decalin, but it isn't. So, in the tetralin Decalin thing. So anyway, it's just one of those things. Yeah.
Talking about those error bars, the ones at the top part don't change, but the ones on the bottom do because of that. Wasn't it because of the ratio? I forget. I wanted to ask you about that too, so I was kind of confused on that.
That's just from the fit. So he does the least squares fit. Each of these points, and this has an error bar on it. So when he does the fit, he has his parameters, and you can take like the derivative with respect to that parameter and get the error from it. If you use a program, it'll just give you the error bars for the fit parameters. These are fit parameters, but it's doing a least squares minimization. And it gives, based on the error in the data, it gives you error in the numbers. So that's propagated error. If he did it right, you know. And he doesn't exactly mention that, that's a standard way to do things. So unless you're using Excel, and then it's like, gives you constant error bars. So you can always tell when someone uses Excel because the error bars are bogus. This looks like an Excel error bar, actually. Like they're all the same, right? So yeah, so that's not true. Like every point is a separate measurement, and you fit the data and gets the error bar. It just happens to be they're all the same here. Some are a little bit different if you blow it up or something. In this case, they're quite a bit different. So this is his death plot, I think. This is the plot. If he hadn't given this plot and hadn't pointed out that thing, which he thinks is going to be important later on, and he mentions, okay, that computer simulations predict this. That tells you computer simulations are bogus, you know? So they can predict anything. So, or I mean, at least that supports that argument, you know. So anyway, it's kind of a nothing paper, you know, but it's good because he used some of the things I was talking about. That's kind of the only reason we look at it. But so, you know, it's not going to cure cancer. But anyway, so that's about it for that. I mean, my answer is like, yeah, it totally doesn't make nothing. None of that plot makes any sense at all. And there's no reason that it would collapse. And there's no reason it would have that value. So this is your key to like ripping this paper apart. You start from this plot and then you start saying, well, if these numbers are wrong, then those fits are wrong. And if you say the fits are wrong, then basically everything starts, it's like a house of cards. You pull out one, the whole thing starts falling apart. So that's the idea here. This is what you do, like, so you'll get, if you get to that point, you'll get emails like every week, some guy, they want to review some paper, you know. This is kind of what you do. Like you have to rip stuff apart, and that's how supposedly you can believe things that are published. That's kind of the basis of science. So the peer review process. In the end, everything can be ripped apart. In the end, and some things, so in the end, I mean, it's like the P thing with what's his name? The genetics guy. And he made up the data, yet genetics is true, right? And he believed it so much that he just fudged the P data, whatever. Right? What is the guy's name from the Middle Ages or whatever? He's like the founder of the scientific method. Mendel? Is that it? Mendel, I think. Yeah, he did the first experiments on genetics of peas. And the data, they proved that the data was made up because it wasn't possible to get such data for the peas. But the idea of genetics was true. Like you mix the one pea with the other, you get the middle pea. And he came up with regressive and whatever chromosome and all that business before they knew what a chromosome was. But anyway, but basically, science is really a belief system that's supported, that people make an argument within the scientific method to verify things they already know. That's kind of what things are, you know, in reality. And this is kind of a, so everyone's kind of making something up. So don't think that the whole thing about they were taught about like hypothesis, and then so you somehow come up with a hypothesis and you go test it, and then it shows it's true or not true. And that leads to some kind of advancement. Basically, somebody has a hunch. That's what it comes, really. I mean, you should just be realistic about it. You know, somebody has a hunch. They're going to get a bunch of data to fire behind that and support it. And then someone else is going to have some other hunch, and then they have debate over it. One of the guys wins, guys or girls. And then like that becomes the belief of science until someone else comes along with another hunch. You know, it just comes down to some kind of random process. And it's based on like you study so much and you know so many equations, you know how to predict things. I mean, look at Dubai and everything's an exponential function. The guy like really loved the exponential function, you know, so and then everything he looked at became an exponential function. But basically he solved a lot of problems. So, and then technology rides on top of that. So you can build things from those models, right? So at least you have an equation. It might not be perfect. It might not be actually true, but basically it works and it can lead to progression of stuff, you know? So it's a dirty process, it's like sausage making. So you got to kind of realize that it's not going to be so clean. Anyway, so these guys might be right in a lot of the things they did. It's a pretty clean analysis and everything. It's impressive. They went through a lot of work, but basically this thing seems to show that what they're saying is not valid, So anyway, for whatever it's worth. So that's kind of the process. The review process is kind of like a everything becomes like a tennis game, like you whack it across the fence and the guy argues back and says like, no, it is true. Then the editor is like the umpire, just says like, yeah, we'll publish it anyway. Whatever. I don't believe the reviewer, I don't believe the whatever. So it just is, and it comes down just to a coin toss, something like that. So anyway, they should have said what was soluble and what wasn't soluble though. And that seems to be a pretty important part of this thing. Because this can't be a late outer shell thing. All right, that's my philosophy for today. Moral ripping apart of science in general. It's also true of these proposals, like you write, like if you can write, so money comes through proposals and they're peer reviewed also. And it's like things get through, they're crazy. And then things that are important don't get through. A lot of it is just the packaging of it or something like that. So it's pretty strange. Anyway, somehow some things actually work. But if you read the best paper that you find, it's a seminal paper, and you look in the acknowledgments, there's no money. Like nobody paid for it because you can't sell a new idea. No one will buy it. If you say like I can make energy for free, they won't give you money to do it. So it's kind of the theme of it. Anyway, so next thing I wanted to go through is this hydrodynamic radius stuff, which is also in this paper. Like he talks about dynamic light scattering, but the first part of hydrodynamic radius is on intrinsic viscosity. So there's just a few things that you may have already heard of if you took intro to polymer, like the Markov equation. So anyway, the point of the intrinsic viscosity is to get this hydrodynamic radius, right? So it's basically going to be the mass of the thing divided by the volume, or the volume divided by the mass. So it's 1 over the C star, 1 over the colloidal concentration is this hydrodynamic radius. Right? And then if you use the Stokes-Einstein equation, you could get it from the diffusion coefficient. So this is kind of Stokes-Einstein. Usually D is KT6 pi viscosity times RH. That's Stokes' law on the bottom, and Stokes-Einstein is this thing. So, but if you can measure the diffusion coefficient with dynamic light scattering, you can get this hydrodynamic radius. Or if you can measure the intrinsic viscosity, which is the original thing, then you can get the hydrodynamic radius.
What's
Right.
the volume of the
Yep.
hydrodynamic sphere over the particles?
No, this is one polymer chain or one sphere. And this is the kind of the mass of the sphere, and that's the volume. So this going to have units of mass per volume. So it's a mass concentration. It's 1 over the mass concentration of one of the things that's a colloidal particle floating around the solution. Right. And then Kirkwood came up with this equation to talk about how to calculate that with a computer for any kind of object that's made up of things that are in positions I and J, like a polymer chain. Right. So it's a double sum over all the things in the chain, and it's an inverse sum because RH is 1 over D, and then D is 1 over R, and this is a transport average. In other words, it's a velocity average would be your harmonic. And so you go to Cleveland, and you go in like 1 hour at 60 and 1 hour at 30, then 30 dominates it because that's kind of how it works out. Your average speed will be closer to 30 than 60. Right. So this is a velocity thing too. It's like diffusion. So it's motion of the thing. So it's going to be an inverse sum. That's the kind of the summary of this thing. If you look at this paper or you look at the equations, they're really complicated. Right. It's not that easy to do this. And this is also assuming that you have no solvent stuck to the polymer. So a big part of this is draining, the draining of the polymer coil. So if the coil is sitting there and all the solvent within it is enclosed, and then it acts as a sphere, that's called a Zim limit of the thing. That's a Zim limit for the viscosity. And if the chain's like there and none of the solvent is stuck, then it moves around kind of freely as a worm, then that's the Rouse limit of it. So there's a Zim limit and a Rouse limit to how a polymer in solution acts. Right. The Zim limit's kind of the simple thing, it's a sphere. And then again, like Bruno Zim was a guy from Brooklyn Polytech in the 1950s or something, but so, and Kirkwood was a guy at Yale in the 1960s. Right? So anyway, so RH and RG are completely different. RG is like an arithmetic average of the square, and RH is a harmonic average of this linear term of just the positions. Right? So they have different values depending on what the thing is. If it's a sphere, RH is a sphere radius. And if it's a sphere, RG is 3/5 of the sphere diameter. So for a sphere, RG is smaller than RH. Or it's the square root of 3/5 of the diameter, which is smaller than 1. And if it's a polymer coil, RH is bigger than RG. So it means the ratio of these two tells you if it's a sphere or a coil. So the ratio, so if you measure scattering and get RG, dynamic light scattering and get RH, the ratio kind of tells you what the thing is, right? Like whether it's a solid object or some open object. Anyway, I think I showed you this before. So Kirkwood, so Onsager won the Nobel Prize, his Nobel Prize star, and then etc. Then Kirkwood never won the Nobel Prize, listed all this stuff on his gravestone. You know? Anyway, it's kind of a funny thing. That's in New Haven, Connecticut. Yale's kind of graveyard or something. But anyway, the RG-RH ratio. So it's basically like from that ratio, people publish stuff on like what the thing is. You know, so basically you can use that number to talk about how the branching of the chains are, things like that. So Stockmeyer is another famous guy, famous polymer person from the 60s. Anyway, so this is the overall viscometer. So it's the thing you'd use to do this. So and all right, so the viscosity depends on the Arrhenius equation for in other words, it's deeply dependent on temperature. So if you do this measurement, you have to be really careful what the temperature is, because an exponential dependence of viscosity and temperature is going to be stronger than this dependence. Right, so usually this thing will be immersed in a big oil bath, like a silicon oil bath, and then it's kept at a constant temperature to do it. So that makes it really messy. Otherwise, it's a really simple measurement. So you fill it up with your solution. It's going to be your highest concentration, or let's see, yeah, your highest concentration. Then you run it. You have a bulb. You push it through this, go up above this line, let it flow through. This thing is a capillary. This is a capillary here going down. So it uses Poiseuille law, and then that gives you basically the viscosity as a constant out of that. Just like here, viscosity is the only thing that doesn't change. So the time that it takes to go through this is proportional to the viscosity. Let's see, to the inverse of the viscosity, like 1 over the viscosity. Longer time would be higher viscosity with that one. And the rest of the numbers are constant. So this works pretty good. So it's pretty, and then when you want to get a lower concentration, you just add more solvent. So you'd start it with it filled up to here. And you get 4 or 5 concentrations by just dumping more solvent in and kind of letting it shake for a little bit, then run it again. So you can do the whole thing in 5 minutes. So that's pretty good. Then from that, you measure what the molecule is. Yeah, so it's a pretty simple way to do this operation. Anyway, so this is the equation that's used to talk about what the solution viscosity or the time. As you say, the time and then the time of the solvent, right? And then you know the concentration because you put in a certain mass into the volume. So this is mass per volume. And then if you measure different concentrations, and you get this intrinsic viscosity, which has units of 1 over concentration. So volume per mass. right? And then that thing's going to depend on the molecular weight. Right, so because the volume's going to depend on molecular weight, depending on what it is. So it'll be like R cubed, and R is going to be NL squared, or n to the 1/2. So you'd have n to the 1/2 minus 1/2 gives you minus 1/2 power if it's a Gaussian chain. And then you can do that for the other expanded coil rods, whatever you want. So you could put tobacco mosaic virus into this. It's a rod. You can measure it, and then you could get the dependence on different size tobacco mosaic viruses and determine that on a nanoscale is a rod. You're just doing this stupid measurement. I mean, so it's cheaper than a TEM. Well, and it's actually more accurate because you're looking at the virus in its native environment, like could be in blood, for instance, or whatever, right? So you can't do that in the TEM, to get so basically it's a simple thing, but it's pretty powerful. This is showing another kind of viscometer without, so this is a cup and bob viscometer, so it'd be a cup around this, and that's the bob or the spindle, which can be of different shapes. So that one's a cylinder, and that one is just a rod that goes into that fluid. This is also the kind of viscometer they use for paint and stuff industrially, except without the cup. So you just stick something into the paint and spin it and see what the torque is on it. So people use that. This is kind of better in a sense because you got a more controlled flow field. So Purcell's law, you have that parabolic flow field in it, so that the shear rate at the wall, shear rate in the middle is 0 because it's a plateau. It's a bell-shaped kind of curve. So the middle part shear rate of the velocity profile is 0 at the middle. And you have a gradient of shear rate across it. And polymers have like shear thinning behavior. So at the higher shear rate, you get a lower viscosity at the walls and a lower, the higher viscosity in the middle where it's no shear. Right, so you have actually a profile of viscosities you're looking at through this thing. This one's a little bit better. It's like a laminar flow. It's got kind of a constant viscosity across the gap, more or less. Aside from the curvature, because the perimeter of that cylinder gets larger, so the shear rate actually changes in the Couette viscometer, but it's better than the Purcell one. So in some sense, this is a better way to measure it. But this is a simple way. You don't need any machine. You just have this glassware. Right. So anyway, so this equation came from originally, the original equation of this came from Einstein, I guess. But Einstein was asked, of all the things that you discovered, what's the thing that you wish you hadn't discovered or didn't have your name associated with it? That's like this equation. Yeah. It's kind of a simple linear equation. And if you think about it, so you can say say you just had bricks and you were just putting bricks into water and you're measuring the viscosity, but you didn't know that the bricks were there. So you just said I had that length and I'm going to flow that way. So I'm going to have a shear this way. So delta X, delta Y is the shear strain. And then that is a function of time. If this is a velocity instead of just moving it, that becomes the shear rate. Right? So it's going to be like that distance over that distance. If you put bricks in, that distance gets smaller. So you could say that distance gets smaller by 1 minus whatever the density of those bricks are times how many bricks, which would be the viscosity times this intrinsic length. So that would just give you a fraction of not brick stuff. Right? Then that would be the effect of the viscosity would be like this thing. If you say the concentration is low, that's the same thing as exponential minus of this. And if you work that back in to this thing, and then say it's exponential of that, then that would be a linear sum, and that gives you this intrinsic viscosity equation. So it's a displacement law. It just means that your stuff is displacing the fluid because you can't measure the actual gap length with the stuff floating in there. Just take that fluid out, you would get this law as a displacement law. It's like the simplest possible thing you could say. It's just bound to fail, right? It's not, this isn't exactly true. Like say the chains drain or don't drain or have interactions, right? A lot of things can happen that wouldn't be like that linear law. So anyway, that said, so that's the simple end of this, even though it's complicated. So this equation, so if you take, so your natural thing would be to divide the solution or the colloid viscosity by the solvent. That gives you what's called a relative viscosity. Normally, that would be called the reduced, because you're reducing this by the solvent. But they call it relative because they have another reduce that somebody came up with, right? Probably Herman Mark or someone came up with these terms, right? So these terms are pretty confusing. You'll see them standardly plotted, right? So you have to kind of know. It's useful if you can remember somehow what's going on here. So I would call this reduced though, but they call it relative. And then if you want to subtract one from that, then you get just this term. It should be linear in concentration, give you the intrinsic. So that's called the specific viscosity. So that divided by that, the relative, then solvent by solvent's one. So it's that thing minus one. That should equal concentration times intrinsic. That's called the specific viscosity. And then if you want to say get rid of concentration, so divide by concentration, that should be a number that doesn't change. So this reduced viscosity, it's reduced by concentration. So I guess it is reduced, but is the relative minus one divided by concentration. That looks a lot like the intrinsic, but it isn't the intrinsic because the intrinsic's really only good at zero concentration. So this should be a constant number that's reduced. It isn't a constant number because there's higher order terms in it. It isn't just so simple as a displacement law. So anyway, so if you look at this in terms of plots, like say you just plotted the solution viscosity versus concentration, well, you'd get to the solvent viscosity. So you'd go down, and then all of a sudden it would go to solvent viscosity and it would just be constant because there's not much change with concentration at really low concentration. And the solvent's much larger than the change, so it just plateaus out there. So you have to subtract the solvent to get something reasonable. When you do that, you find out this is like depends on concentration. And then it depends higher once you get above the entanglement concentration. And then if you reduce it by the solvent, then you have this thing like, well, here this should go to zero because it should go to solvent at zero concentration. But then the scale here becomes like one becomes magic for some reason. I mean, I don't think anybody knows why, but basically, when this reaches one, you're at double the solvent viscosity. And when you're at double the solvent viscosity, roughly that's where you have this transition to entanglements. So somehow doubling the solvent viscosity is where the entanglements happen. I mean, that hasn't been explained why that happens there, but that's like a rule of thumb. And so this should go to zero. The slope of this thing should be the intrinsic viscosity. And if you go to reduced viscosity, this should just be a constant number because that's the slope of one. So if you pull out concentration of the one, that goes to just flat. And that's just the intrinsic viscosity then. Right, so the idea is like, once you lose that power one dependence, this thing goes to this intrinsic viscosity here. When you get zero concentration, you extrapolate to that. That's kind of the way this works. So the reason that you're going through this whole thing is because you can't see anything at low concentration because the solvent viscosity dominates. That's the key element here. So if you just measure the viscosity, someone shows you that plot, you'll say like subtract the solvent from that, or divide by this, subtract the solvent from that so I can see what's going on down at the coil size of the thing. Right, so anyway, so people have come up with these power series expansion of that guy. And then this thing starts to look like an exponential, like 1 plus x plus x plus x squared by 2 plus whatever would be like a power series. So somehow you can think of that as an exponential. So you get like an exponential term. So people have come up with different ways to account for the nonlinearity of the thing. Martin equation, this power series thing. So this looks like a viral expansion, kind of. So something about, in viral expansion, we're dealing with the osmotic pressure, and then we do a concentration series, and you get these prefactors. So you think like well, these prefactors must have something to do with, so intrinsic viscosity has to have something to do with the, especially because the second Vierel coefficient is the excluded volume of the thing, which is the same thing as this, right? In other words, this is kind of the excluded volume of one coil. So it starts to look like this is the same thing as a Vierel expansion with osmotic pressure, because B2 is a volume, effective volume, and then this thing is kind of a volume per, right? So, but they're different because this thing is, this is a dynamic measurement, remember, so this is a measurement in a viscometer. It's not a measurement, it's not a thermodynamic measurement. And the osmotic pressure is a thermodynamic measurement. And thermodynamics and kinetics never mix. That's like the rule. There's a barrier between the two, right? So nonetheless, people like go ahead and kind of make connections between this and the Vierel expansion. This, because it's kind of, they're both volumes, just like volume squared. B2 is volume, B cubed is volume squared, B3 is volume squared, so similar. So there's a variety of equations that people have used. I mean, you'll see them. This Kramer equation is kind of famous. Huggins is like Flory-Huggins equation guy. And then, so basically there's some equations, right? There's books on this too. It's Jameson and Utraki book on this business. So this became, all right, it's important to polymers, also really important to biopolymers. Like this became like kind of one of the main areas of looking at proteins and viruses and things, because it's such a simple measurement to do. So says the Jameson, both of these books deal a lot with biological systems, but anyway, so this is showing like, so the specific viscosity is let's see, specific should be a power 1, and reduced should be nothing. Reduced should, or yeah, reduced should have no slope at all, I think. No, specific, they're both should be power 1s. Right? So power 1, so reduced should have no slope to it. These aren't plots going to go with that. Specific should have a power 1, reduced should have no slope. So this is, so you have to be careful what's being plotted. This is reduced, so it should have no slope, should just be flat. But this is this acetylated starch. So it's got it's starch that becomes soluble in water because they put acetyl groups on the surface of it. And then different molecular weights. So this should be flat. It's got a slope because it's got this second order term or maybe higher order terms in it, right? And it's fit to some different functions. It's from this viscosity book, right? So basically, people are kind of looking at this, right? I even put it here, specific by concentration means it should be flat, right? So people have looked at this business. This is also reduced, so this should be flat too, and it is at low molecular weight, and at higher molecular weight it deviates. Right? This is for also polyelectrolyte, like polyacrylamide, something, blah, 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 blah. So basically polyelectrolytes don't behave that way. So with polyelectrolytes, the thing that's going on is as you increase the concentration, you're also increasing the charge, the counterion concentration in it. So they naturally are going to either attract or repel. Then as you increase the concentration, that attraction repulsion disappears because you're screening the charge with the Debye screening, then they become normal polymers. Right, so the actual beast that you're looking at is dependent on what concentration it's at, because the charges are screened, so it becomes something different. So it goes from like a rod down to something like the coil as you change the concentration. Right, so anyway, things happen. Like I guess that's the point of this. This is a Witter ionic polymer, so it's got a negative charge on the carbonyl, positive on the amine. Right, so it's got both charges. It also has, this is also the reduced, so this should be flat. And then if you put it in water, if you put it in glycol where you can't have, so these are different dielectric constant. So the charge effect disappears to go to glycol, and in water, it's got a high dielectric. So it's got a bigger effect, bigger charge effect. I forget who did this. It doesn't say, it's just from that book. But basically, so people have looked extensively this stuff. In fact, whole PhDs, many of them have gone through just doing intrinsic viscosity measurements for different things. These are also polyelectrolytes. That's showing how this should be constant again. It's not. Then so what do you do? Like say you want to say that when this thing's at low concentration, when this thing's at low concentration one, whatever that is, then it would be like a rod. And then when it goes to high concentration, it should be a coil, right? So how would you deal with that? So basically, the mass, so you have the volumes of mass 3 by dF, then you end up with this equation for the intrinsic viscosity, which is the same as the Mark-Hoank equation. So if it's dF is 2, this is 1.5 minus 1 is 0.5. So the intrinsic goes in molecular weight to the 0.5. And then if this is 1, so if it's a rod, this thing goes to molecular weight to the 2. So there's a big difference between 0.5 and 2. So you can distinguish between a rod and a coil, a Gaussian coil. And then if dF is 3/5, dF is 5/3, this is 9/5 or 1.8 tenths, so it becomes 0.8. 1.8 minus 1 is 0.8. So you have 0.5, 0.8, and then 2 for rods. And if you did discs, you could get 1, I guess. 3 by 2 would give you something for discs. I guess it's 0.5 for discs too. So discs and Gaussian coils have the same slope, 0.5. Right. So this rod is 2, excluded volume is 0.8. So you can start looking at the molecular weight dependence. That's a Mark-Hoank alpha A term, right? So it's Ka, the 2 Mark-Hoank coefficients. So these are tabulated in the Polymer handbook, the K and the A. And you'll see that the A values vary between 2 and 0.5, basically. So kind of somewhere in that range. And then basically, if you know those 2 parameters, if you measure this number with this weird machine, a simple machine, you can get the molecular weight. Right, so that's called the viscosity average molecular weight. So it's higher. So you have number average that you get from osmometry or osmotic pressure. There's the weight average you get from scattering. So that's higher than number average. And then there's this viscosity average is higher than those 2. It's the next higher average molecular weight. And the dependence of it is the A dependence. In other words, what moment you're getting is the A moment of the molecular weight. So anyway, so those are the 3 standard molecular weights people have. MW, MN, MW, MV, which comes from this thing. So chemists, every chemist, polymer chemist kind of has this thing sitting in their lab to just do a quick measure of the molecular weight. Like that's pretty standard. So chemists like this thing. Anyway, so this is what Einstein came up with. So this isn't the concentration, this is the volume fraction. So I put the same symbol here, but I think I changed it somewhere. I guess I didn't change it. Oh yeah, here, it did change. Right. All right. So this is the volume fraction. So volume fraction is related. So volume fraction is going to be the mass fraction divided by the density. So Einstein calculated for spheres that's 2.5. And then, so last thing, this equation, this equation was used by a guy named Guth and Gold. And then they said modulus, and then it becomes a composite material. And the modulus of a composite would be like 2.5 times. So just take Einstein, swap out modulus for viscosity, and then you get the modulus of a composite with randomly arranged particles in it. And then the Guth and Gold is 2.5 volume fraction plus 14.1 volume fraction squared. So it includes a squared term. But it's basically the Einstein equation lifted and just parked into like modulus equation. So you'll see that a lot. Any kind of nanocomposite or any kind of composite, we're going to say like the modulus is a modulus without the stuff, and then 1 plus 2.5 times that plus 14.1 times that thing squared, the volume fraction. Anyway, you quit there. So that's about it. email me if you got problems with the homework, so.